All right, now let's talk about a confidence interval for two proportions. And what I have here is I have two populations. Within the first population, I have N1 as that population size. So the total population, there's N1 as the sample or as the population size. And then out of that N1 population size, X1 of those are successes. So that the proportion of successes in the population 1 is P1, which is just X1, the number of successes, over N1, the population size. In the same way, the second proportion, P2, is the total number of successes in population 2, which is X2, over N2, which is the population size of population 2. So what I'm interested in is actually the difference between these two proportions. So P1 is the first proportion, P2 is the second proportion. I want to know what the difference is between those two proportions. So for instance, this could be a population of Democrats, this could be a population of Republicans, and I want to know what percentage of each group feels a certain way about a certain issue. Maybe it's the overturning of Roe versus Wade or something. So I'd go out and I'd ask a bunch or the entire population of Democrats and the entire population of Republicans if they agree with the overturning of Roe versus Wade, and then I'd just create these proportions. And I don't know, maybe those proportions are the same. Maybe the same amount of Democrats feel a certain way about it as Republicans, or those proportions might be different. I'm interested in what the difference is between those two proportions. So what I do is, because I can't actually go out and ask every single Democrat or every single Republican, I'm going to take samples. So I'm going to take samples from the population. So I have sample 1, which comes from population 1, and I have sample 2, which comes from population 2. Each of those samples has a certain number of successes and a certain number of failures. The best point estimate for the proportion of successes in population 1, P, is P1 hat. So the best estimate for P1 is P1 hat. And likewise, the best point estimate for P2 is P2 hat. So the best point estimate for the difference in the two population proportions is P1 hat minus P2 hat. So what I'm saying is the best estimate of P1 minus P2, which is the population difference of proportion, is P1 hat minus P2 hat, the difference in the two sample proportions. All right, so here we have a scenario where we have the two samples. One of my sample sizes is 240. That would be like N1. The other sample size is 285. That would be N2. And amongst the 240, I have 24 successes. That would be X1. And amongst the 285, I have 27 successes. That would be X2, respectively. So we're going to construct a 90% confidence interval for the difference of those two sample proportions. Or actually, we're creating a 90% confidence interval for the difference in the population proportion, but we're going to use the point estimate of the difference of the two sample proportions. So since we're trying to create an estimate of P1 minus P2, that is our statistic, or our parameter. The parameter that we're trying to estimate is P1 minus P2. The statistic that we're going to use to estimate that is P1 hat minus P2 hat. Now, if you remember about sampling distributions, if you take a bunch of those sample statistics and create a histogram, you get what's called a sampling distribution for that statistic. And the sampling distribution for P1 hat minus P2 hat would be centered at P1 minus P2, the population parameter. So that's why I have this bell curve, which is centered at the population parameter of the difference P1 minus P2. Now, my specific difference in proportions from my samples, P1 hat minus P2 hat, is going to be somewhere in this sampling distribution that's centered at the population parameter P1 minus P2. Now, these are my two sample proportions. 24 out of 240, that's X1 over N1, minus 27 out of 285, which is x2 minus n2. So this is my difference in the two proportions from these two samples that I'm giving. So this is going to be my point estimate, P1 hat minus P2 hat. This will be my point estimate of P1 minus P2. So what I'm going to do is I'm going to create a confidence interval, and that confidence interval is going to be centered at my point estimate. And what I'm going to do is I'm going to try to capture 90% by adding a certain margin of error and subtracting a certain margin of error. I'm going to try to capture 90% of all the sample proportions in this sampling distribution of the differences of sample proportions. So I'm going to try to capture 90% of all the sampling differences of proportions. All right. So let's see. Let's just change these to decimals. That's 0.1 and 0.0947, so that's 10% and roughly 9.47% are the two sample proportions. And when I subtract those two, I get 0.0053. So this is my sample statistic. This is my point estimate for P1 minus P2. So my point estimate for P1 minus P2, the difference in those two population proportions, is 0.0053. And like I said, what I want to do is I want to create an interval around that can capture 90% of all those proportion differences of sample proportions. So I need to know something about the spread of this thing, the distribution. So I need to find the standard error of the P1 hats minus P2 hats. And here is from the central limit theorem what the standard error of that would look like as long as it passes the success-failure condition in both samples. So as long as the success-failure condition holds in both samples, this will be my standard deviation for my sampling distribution, or my standard error for the P1 hats minus P2 hats, that difference of proportions. So because I know that, and I also know that it's going to be normally distributed if the success-failure condition is met, that means that I'm looking at this thing being actually normally distributed with a standard error equal to this here, P1 times 1 minus P1 hat. So P1 hat times 1 minus P1 hat over the sample size 240, and then P2 times 1 minus P2 hat. P2 hat minus times 1 minus P2 hat over the sample size 2. And when you do that calculation there, you get this as the standard error. So we have the standard error, and we have the point estimate. So to create a confidence interval, what we do is we take the point estimate and we add the margin of error and we subtract the margin of error. To find the margin of error, I have to multiply this standard error by the critical z-value. And the critical z-value is going to come from this table. So the margin of error is equal to that z star, which is the z-value separating whichever confidence region I want. In this case, it's 90% in the middle. And I want that to be multiplied by the standard error of the P hat 1 minus P hat 2s, which comes from this sampling distribution here. And let's see, that means if I calculate this, I can multiply whatever the z-score is for 90% in the middle by that standard error, which I have here, and that'll give me my margin of error. Well, let's do that. The z-score for 90% in the middle is 1.645. That's this z-score here. And the margin of error I have is 0.026. When I multiply those, I get 0.04277. And that is my margin of error. So to the point estimate, 0.0053, I'm going to add that margin of error to get the upper bound of my confidence interval, and I'm going to subtract that margin of error to get the lower bound of my confidence interval. So for I'm going to assume then my confidence interval is going to say that the difference of those two population proportions is somewhere between the point estimate plus the margin of error and the point estimate minus the margin of error. And those are the numbers. 0.0053 is the point estimate of the difference. That's the sample the difference of the two sample proportions. 0.0428 is the margin of error. And then I add and subtract it, and this is my confidence interval. So there we've created the confidence interval for the difference in two population proportions.